All right, we have the new problem set up. I think all of you have until the end of the day, end of Tuesday, to submit the other one. Oops, this problem's at 4. And I've already uploaded this to the Canvas. But what we're going to do today, we're going to derive all these equations for inviscid flow. They're basically, this is, so we'll talk about inviscid flow and what that has to do with irrotational flow. Irrotational flow means no vorticity. But we'll show how these are related. They're all associated with what's called a high Reynolds number. We're going to introduce this idea of, so a lot of you have done potential flow, maybe if you took undergrad fluid mechanics. We're doing a slight variant called complex potentials, which has the same, basically you can do, keep the information about potentials and streamlines in the same equation. That's the utility of it. The homework has basically 5 problems again. The last 2 problems, they don't fit here, but they're about, one is if you have a boat and it's filled with water, how do you use that boat to actually move if you don't have a paddle? And we talk about, hey, if you drill a hole in the bottom of the boat, if the water in the boat's higher than the water down in the, in the pool, then you're basically can, drain water at some velocity, and you can use conservation of linear momentum to basically push your boat forward. The other question is how do you, if you're in a vortex, how do you arrange your ballast, your center of mass, center of gravity versus center of buoyancy, so that you actually don't get sucked into the vortex? So we'll derive the potential flow equations for a spinning vortex. Not this time, but next time. So you won't have everything you need to know this week, but about 2 weeks. We're grading these things, the homeworks, so I hope to have it done end of the week, and then we can give it back to you, and then we can figure out the good quiz time. We have about 2 homeworks left. Realistically, it might even be 1, because we have the course projects. Definitely at least 1 left, maybe 1 to 2. And I want to do 3 homeworks, but we just had too much other stuff going on. All right, so we have a new unit today. Oops. That page. And the last couple of sections we did were all about viscosity. Like the whole reason you got, you had basically any kind of flow at all because the action of viscosity transferred information about a moving boundary to very far away. Here we're going to basically show how we can solve problems without viscosity. So the Navier-Stokes equations become what's called the Euler equations. We talked about them very briefly last time when we, a couple times ago when we did dimensional analysis. We non-dimensionalized the governing equations. The Euler equations look like this. All right. And so note that there's no viscosity term that's gone. The viscosity is 0. So there's something called superfluids. Which basically, like liquid helium, and you can imagine you had to be really, really cold for it to be superfluid. But there's really amazing things for superfluids. Like if you look on YouTube, there's these, their capillarity has nothing to work against because fluids just always flow. So if you have a cup of helium, liquid helium, it basically, capillarity causes, you know how capillarity causes, if I had a glass of water, capillarity causes it to have a hydrophilic contacting with a glass. Well, if you do that with liquid helium, it's just going to keep on coming out of the glass. It just always goes back, it always goes, because there's nothing resisting the flow. It also has some weird properties that actually can penetrate through like materials. So if you have something that's slightly porous, all the helium will basically go through the little pores because there's no viscosity. So it'll drip through a solid, essentially. But unfortunately, you have to have really, really low temperatures. So there's still, I would say there's still not any big applications for things that are superfluid. Yeah.
Are superfluids similar to supercritical fluids, or is supercritical like a whole nother topic?
I know something is supercritical if it's like there's a PTV curve thermodynamically, and there's like one point that is like a solid, a liquid, and a vapor phase. Those also seem to flow a lot, but I think they're different. Because a superfluid is a liquid, whereas a supercritical fluid, it's like a liquid and a gas, and it's like you have this critical factor. Do you know about it?
Does gravity resist the helium from flowing out of the glass? Because you said it keeps coming up.
Oh, the gravity is in some ways gravity's. So the surface tension, if it's at really, really small scales, like you could have a little layer, and it's basically small enough that gravity doesn't matter in that thin layer. I mean, it takes a long time for it to come out, but if you're thin enough, it won't stop you. Yeah. And they've done these experiments in the space shuttle too. If you have like a wet towel and stuff like that, it does very, very weird things without gravity. So we take viscosity for granted. It keeps a lot of weird things from happening. But this Euler equation, I think there's some people in Aeroastro. Anyone still in Aeroastro in this class? Aeroastro? And that one person left. Aeroastro, you have super high Reynolds numbers. Like, airplanes are like hundreds of thousands. So Euler number is usually pretty good. So this yields insight into high Reynolds number flows. Because as we saw before, the non-dimensionalized version of these equations we have a 1 over Reynolds number here times R times this term. Okay. So as Reynolds number gets high, we get closer and closer to Euler's equations. All right. It's still not super easy to solve, so there's a couple limits. For example, number 4 and number 5 of the homework are what we call steady Inviscid flows. Steady meaning the time derivative basically is 0 and there's no viscosity. Okay. If you have steady Inviscid flows, we're a very short derivation of the Bernoulli equation. This is the equation you have left if you get rid of the unsteady term. All right. We'll call this star. So you basically have the convective acceleration is balanced by your pressure and whatever gravitational force you have. And because we usually deal with gravity, we're going to write F as the gradient of some function psi. In physics terms, they call this gravity being conservative. Not all forces can be written like this, but gravity can. And you worked on this, I think, for your homework. In this case, gravity can be written as psi is equal to negative rho g dot x. Okay. Where psi is some scalar function. It's not a vector. It doesn't depend on direction. Then we're going to use an identity that we showed in homework 1. Okay. So let's substitute that into our governing equation. Oh, I should mention, before I get too far ahead, the office hours today, so let me just put it up here. Office hours, I'll be there from about 1:30 to about 4, but the 60 undergrads I have also have a quiz on Wednesday, so it might be a little festive. All right. Sorry, plus. All right, so all I've done is replaced this convective acceleration with these two terms. And so remember the units of all this stuff. The original equation star was units of force per volume. All right. So we're going to take basically a scalar product of that vector equation with a velocity. So force times velocity, that's going to give us power per volume, or energy per time per volume. So U dot del. Okay, a couple things. This second term disappears when I take the dot product because that term is perpendicular to U. You know, U cross something is perpendicular to U. And so if it's that has no component in the direction of U, so that disappears. So what I'm left with is this. And this equation has energy per time over volume. Okay. So basically, if I have the amount of volume in the system, I can tell you how much energy is changing. And what this says that basically, all right, this physically, this means the gradient projected on the direction of this motion. We call that a streamline. The direction motion, streamlines are basically parallel to your velocity field. You can imagine if this is my velocity field here, then basically I'm looking at I'm saying that this quantity in parentheses doesn't change as I go along this streamline, because I'm saying U dot this thing is equal to 0. So this thing in the quantities doesn't change, and I'll call that a quantity H. So H, which has units of energy per volume, is constant along streamlines. So you can imagine if I basically look at my fluid particles, I can count the amount of velocity, kinetic energy I got, pressure, and the amount of any kind of gravitational stuff, gravitational energy. And that the sum of those three is not going to change. So basically, physically what this means is the change in kinetic energy is balanced out by the change rate of work against pressure. What I've done is move the gradient sign into the parentheses, and this is the rate of work done against gravity. Okay, and we have the sum of these three are 0. This is a statement of conservation of energy. And when your Reynolds number is high, you're not really losing much energy to viscosity. So it's used when viscous dissipation is, can be ignored. This is true along 2 points along a streamline, but we're going to show for irrotational flows, for flows that have no vorticity, it can actually be true between any 2 points. So they don't actually have to streamline. Physically, a streamline means if I put a little, put a little blue dye here, that dye eventually goes over here. It basically follows the path. But for irrotational flows, this is true between any 2 points. Yeah.
That last term says rate of work done against gravity and can only be what?
Oh, sorry. This is 2. I was just starting a new sentence. Basically, above it's just conservation of energy, and I'm just saying it can only be used when viscosity is small. So, for example, for the homework, there's some tricks you can use to apply Bernoulli's equation. For example, let's do flow through a spillway. A lot of problems, including the problem on the homework where you have the boat that's releasing, the boat's filled with water and is releasing fluid. So let's say this is the water surface. So this is the land here. I got my velocity u here. Originally it's a height capital D, and then it becomes a height little d. So you can pretty much calculate everything that's going on here. For example, if you know what the incoming velocity is, mass conservation tells us that basically we got mass conservation. You can consider this per unit depth into the page for these 2D problems, or that the depth into the page, or that depth W is equal to 1. So mass conservation tells us that basically what's going in, V times the area, which is per unit depth in the page, is V times D, is equal to what I call U times little d. So that tells us what basically how V and U relate according to the geometry. And imagine we have a streamline. So imagine you have like a little particle here that goes like a little rubber ducky, and it's traveling down here. That's a streamline because fluid is always parallel to this ducky's direction, and we choose it at the water surface because at the water surface there's no pressure contributions. So you're going to call that a point 1 and a point 2. and basically you got P2 is 0 and P1 is 0. You also did call this P atmospheric, but usually those pressures are really small compared to any kind of hydrostatic stuff. So rho v squared plus now we had to name another variable here, so I don't have to write the z's. We'll call this a height h. Plus rho g h, and that goes into the base of the pressure at 2 plus 1/2 rho. I call that u2 squared or u squared, and then there I call this if I call this z equals h, and I'll call this z equals 0. There's no gravitational term there, and these are 0, and so that leads to that the velocity of the exiting fluid simply depends on the height. So notice a couple things physically. That lake on the left, on the top of the mountain, the amount of water in that lake didn't actually affect the flow speed. Only Bernoulli's equation is the equation between 2 points, and it says that your velocities only depend on in this case, on the height differences. So I could have that lake being like a mile wide or just a few inches wide. I essentially have fluid flowing downhill. In other words, basically, fluids follow kind of projectile motion. Like if I basically drop a pen from this height, the speed that it hits the ground is going to also be u equals squared root 2gh, because the gravitational energy I have per unit volume up here is basically released into kinetic energy as it flows down. So Torricelli's law and any fluids flowing by gravity are just stating that fluids are going from high to low. And it might as well not even be a fluid. It could just be like a ball of mass m. Okay. So this is called Torricelli's law because I think this was, they kind of knew these ideas before they did all this. Navier-Stokes certainly. And the volume flux you can write as Q is equal to U times D, which is equal to D over square root of 2gh. Okay, and this yields Q in terms of flow geometry. Okay. Yeah.
Your little d, your small d, where is that on the diagram again?
Oh, it's this height. It's the height of the I'll just draw this inside. D. That's better.
Professor, are we assuming that velocity in the entire cross section is same?
Yeah. So there's no effects of viscosity. So you don't have any things like this is going to be a weird homework. In all these homeworks, anytime you have a solid boundary, you still have like a velocity vector right next to it, because the Reynolds numbers are reduced so low that the boundary layer is basically just like doesn't exist, and basically we just flow easily past boundaries. If you don't have viscosity, boundaries don't really affect you anymore. But this is basically the only kind of way to solve. Basically, Navier-Stokes equation you can solve in a couple limits. You can solve what we just did, which is unidirectional limits, where the flow and the gradients are different, velocity gradient are perpendicular. That you solve 2 or 3 problems. Now we're going to solve for a flow where there's no viscosity. And if there were more time in the course, we'd do a whole homework on low Reynolds number stuff. But I have a feeling we're not going to get to it. All right. Uh-huh. Yeah.
Big D and the little d,
Yeah.
those are always going to be perpendicular to the surface of the water? Is that the way that's where you're drawing it?
Yeah.
It's different than H, which is Z.
Yeah, H is just kind of the difference in height. I had to draw an H because I didn't describe these.
Right, but the D in terms of H would be cosine of something or
Oh, you have to be really precise. Yeah, D is just giving you an idea like how wide the channel is.
okay.
Yeah, is it full influence? It's supposed to be in meter cube per second, no?
Oh, Q? Okay, it's because everything is flow unit per unit width into the page. So you can consider there to be a 1 here, which gives you the right units, or you consider it to be, or this can be flow rate. Let's just do this. Liters per time per unit width into the page. So 1 over meters. Let's call 1 over length. Because this is a 2D problem. Okay, I want to give a few. Bernoulli's equation can also cause some pretty weird. There's a lot of biology textbooks that talk about how Bernoulli's equation is used. I want to give you a few problems that give you some intuition for how it interacts with like moving bodies past a house. Basically, imagine you've got this house with basically doors on all 4 sides. Oh, this again. There's a door back there, and there's a door back there. Okay, and let's say I got fluid blowing past it. Okay. So a top view of that house looks like this, where I'm going to have the doors here. There's no wind. And let's say I don't have my HVAC system on. I think for example, most Georgia Tech buildings have positive flow on the inside so that when we open the door, stuff doesn't all blow in, but just a little bit. But basically, if we don't have the HVAC system on, basically, the doors are going to stay closed, right, because there's no difference in pressure. All right, so question for you, and you can talk to your neighbor. If I have the fluid flowing this way, which doors open? Why don't you talk to your neighbor about it, and let's take a vote. I want to know which of these doors open. Let's say they're swinging doors. And we'll call this A, B, C, D. Yeah. They're like really nice doors, really expensive ones. But I just want to know which one's open. So why don't you think about it, talk to your neighbor, and let's take a vote. Yeah, this whole homework is going to be there's no viscosity. That we're only looking at the effects of pressure and inertia. And you have to use, in some ways, you have to think about the Bernoulli's equation. Yeah, the inside is, well, basically I just have the same cases here, except now I'm just blowing. Like I haven't changed the inside case at all. Yeah. There's 2, I'm going to tell you a hint, 2 of them open. Think about it and talk to the person next to you, and then we'll take a vote. Let's ignore internal flow. Yeah. Flow separation is only due to viscosity. Without the effects of viscosity, flows do not look very interesting. I got your extra credit email, but I haven't. Yeah, and it changed something else. I think everyone else glosses over it, so I think probably the effort you put is enough, but because it's like not.
And high pressure is low pressure. It's gonna just go back.
Oh, I need to look at it. I need to look at it carefully. Let's talk about it. Let's talk about it later.
Yeah.
All right.
But if they can open either way, then it becomes tricky.
Okay.
The pressure would just balance out.
So maybe they were swinging around. But
All right, so closed. All right, class vote. We could do this on. Okay, who thinks which one do you think goes open? Just someone call it out. C and D. All right, who votes for C and D? It's like I don't know, 10 people. All right, A and B. Who thinks A and B open? I've got the remainder of people. I guess you're gonna hedge your bets, huh? It's like about 7. All right. Okay, so let me tell you something about when there's no viscosity. So, for example, you've all seen these images of like a basically flow past a sphere. So in reality, flow past a sphere has like if you throw a baseball and stuff like that, it has this thing called a turbulent wake. But this is all induced by viscosity. Specifically, you have this. All right, there's this really thin boundary layer where basically you have vorticity. That's called the rotational region, and that vorticity shed, and that goes downstream. So vorticity, I know you calculated vorticity for some previous homework, but it's almost like density. It's something that the fluid has, and it carries it it goes with it. So basically, once you have vorticity, it's shed as this stuff is going away. And this is there's the boundary layer, and this is like this is a sports ball. So something that you're going to play, not like if bacteria were to play baseball, that would be not going very fast. So the problem is once you have no viscosity, all flows have to be basically symmetric left and right. So this is with viscosity, and this is no viscosity. Okay, so a couple of things are resulting from that. One, you still have bluff body drag. So we're actually going to calculate that when you have no viscosity, this is pretty surprising. We're going to spend maybe 1 or 2 weeks calculating this, and you have to redo it in your homework. There's something called D'Alembert's paradox. Oh, we actually have real French people here. How do you say that? D'Alembert? D'Alembert. Okay, paradox. He's obviously French. He basically said, so historically, I think potential flow, this idea of no viscosity, this came before Navier-Stokes equations. Navier and Stokes actually, I think, lived in the 1800s, but D'Alembert was like early 1800s. And they basically came up with all this math for potential flow, and they found this really weird result that there's no drag on cylinders. And we're going to prove that over the next few lectures. And that confused people for a very long time until Prandtl came along and said, hey, because they were thinking, hey, they had this idea of Reynolds number. They said basically that you have a high Reynolds number, so it seems like viscosity is really, really negligible. But in actuality, you have to look at your length scale that you're talking about. And then Prandtl, German guy, he basically said, hey, even though fluid dynamics, we have this radius and you have a length scale and you have a Reynolds number, what matters about whether your viscosity is dominant or not also depends on the length scale of like the little flow regime that you're caring about. So if you look really, really close to the ball, you have to go from no slip to slip. And in that region, you do have what's called a rotational region where you have viscosity. So when you have no viscosity, you have a couple of things happening. You have basically, these are called stagnation points. Stagnation points mean where the P is the maximum pressure. Basically, if I were to put like a little pressure probe and I wanted to break, that pressure probe to break, I would put them here and here. You can consider those to be the places on your car where like the insects like go there and they die. They don't like go around, but they go because that is basically just have too much pressure for their little exoskeletons, so they die in the front. And I think that makes sense that they die in the front, but because there's no viscosity, the front and the back have to look the same, and there's actually a stagnation point in the back. So those are basically where P is equal to P max, and as a result from Bernoulli, if pressure is the maximum, remember we're talking about conservation of energy, if you've got maximum energy, static pressure energy, then you have the U is equal to U min. And conversely, at these 2 points, you have your pressure is equal to P min because your U is equal to U max. Okay, so these are the points are where the doors open. So let's correct this here. We got basically doors, and they open outward. Okay, so so this is correct. All right. So doors at C and D swing open because they're outside the stagnation points. The stagnation points have the smallest pressure. In fact, A, you're going to have to make sure you keep the doors locked so they don't swing inward. And similarly, weird enough, similarly with B, you only get, so in actual flows with viscosity, you actually have a low pressure zone here, and that actually causes increased induced drag. But you don't have that for no viscosity. You have pressure, high pressure on both sides, which is unfortunate. Okay. All right, so that's a little lesson about physically what that does around solid boundaries. And if someone wants to do a course project on that, that's kind of available. All right. So let's say we have a floating canoe in the water, and let's say we decide to go on a day that's blowing really fast. So we'll call this a point A and B. So I have a question for you. What is the steady state position of the canoe if the velocity is going to go this way? Velocity is coming in for the bottom. So basically, I'm like rowing my canoe upwind. What's the steady state position? And thanks to everyone for voting. Steady state position. All right. So we got 2 options. Why don't you talk about it with your friends and talk about the stagnation points. This is a different case than the previous one because here the canoe can actually rotate. It can move. Inviscid. Oh, you just have to stroke once. All right. So I heard a couple of things. I heard people say, hey, this minimizes the drag, which is true. But let's take a vote. So who thinks it's the left one? Raise your hand if you think it's the left one. Like 6. And all right, then who thinks it's this one? Why do you guys think that? Like 14 people. What?
The pressure in the front and the back is increased there. So it's in that well of.
Yeah, this is a case where you had to, so basically, imagine it's in this intermediate configuration. Then in this case, you got stagnation points at points A and B. And they're going to have a resulting torque. That aligns canoe perpendicular to the wind. So basically, this is the only this is the maximal drag, but this is the only stable configuration because you can imagine if you got basically anything that varies from this, this is going to go this way, and this is going to go this way due to the high pressures at those points. That's what Bernoulli says, but I've actually never rowed a canoe in the wind, so that would not be a bad demo. What we are at? I know how I skipped so many points. Let's just forget these numbers here. The last thing. Oh, I forgot to bring my ping pong ball in the funnel. Yeah.
Because like the canoe is on the water, but it's like the wind is blowing around it.
The water is just like a frictionless surface. Yeah, imagine the water, it just slows down the canoe's motion. But so this is wind. But I think if you had water, no, I don't think water totally works because then it's just going to translate with the water at constant velocity. I think it has to be wind. All right. I got to bring my ping pong ball next time. I'll bring my ping pong ball next time. But in nature, there's a lot of other examples with Bernoulli's equation. Like these I was going to say varmints, but that's just like what Wile E. Coyote calls them. Groundhogs? What's a varmint? Varmint is like a pest or something like that.
Yeah.
Okay. But there's groundhogs. They basically build these little underground tunnels, and they basically can generate this circulation. They'll build a tunnel and they'll have a pile of dirt here, and so basically this pile of dirt changes the pressure, makes the P1 here and P2. P1 here is going to be different from P2, and that will generate flow. So a lot of these structures have air conditioning systems that keep them enough oxygen just by the way they're designed. Okay. They definitely have a hole, but I think the actions of viscosity might start to be kind of important for ants. Like those holes are not super big, but yeah, ants also have they basically have these things too. They have these anthills have something like that. So you can imagine as you go here, you're gonna get circulation throughout here.
Is it similar to how ancient civilization generated AC?
Yeah, and there's even some designs in Africa that African architecture that uses Bernoulli for basically natural. I don't think for natural convection. And I think it's really kind of like all the rage these days for people to try to design architecture that uses these ideas so that when the wind blows, it actually creates convection cells on the inside. All right. Okay. So the last two problems of the homework are kind of like scaling problems, and this is pretty much what you need to know for the scaling. I'm going to try to bring my ping pong ball demo. I have a couple of demos associated with that. Try to bring those. All right. So for problems 1 through 3 for the homework, we're going to have to deal with solving velocity potentials. But before we get into potentials, let's talk about circulation. So this section is going to be on solving velocity potentials. So basically, you're going to use these phi to get u. So before we get into the mechanics of how to do that, because we're doing it. We're not doing the undergrad level. We're not doing the 2D version. We're going to do the 3D version, which involves vectors and tensors. Before we do that, let's have a little intuition for what happens to these kinds of flows. So Kelvin's circulation theorem. All right. So Kelvin's circulation theorem says, hey, if I basically have 2 points. Let's say I have this closed curve C. Kelvin circulation theorem that says that d sigma dt is equal to 0, where, sorry, not sigma, gamma, capital, I think that's capital gamma, yeah, gamma. Where this is called the circulation. So the circulation is kind of like adding up all the velocities if I were to take the velocities all around this curve. And it's saying that, hey, there's no net circulation. You can imagine physically it's associated with like spin. If I basically have something that's going to be rotating, I'm going to have some non-zero value for there. But this says, Kelvin circulation says if we got basically inviscid fluid, the circulation doesn't change. So the full statement is this. So the curve is going to be able to move and deform. But we're dealing with inviscid fluids, so the viscosity is 0. If basically we have if the only body force is due to conservative force, which is gravity, then Kelvin said his theorem was that the circulation doesn't change. In other words, d gamma dt is equal to 0. All right. So why? And you can imagine, like basically, U doesn't necessarily U doesn't have to be parallel to dl. So basically, U could be like, I don't want to make it perpendicular either. U in this direction, and at some little point later, you got U plus du, and I got basically this dl region. But I'm saying the U dotted with basically the direction of, I can call that L, the direction of the tangent around the curve, the sum of that U's are going to be 0. Okay. So why does that, so you can see this is going to involve some elements from Bernoulli to see why this is true. And we need to know this because this circulation is related to vorticity. How much circulation we have is related. So basically, if we're saying we don't have viscosity, whatever vorticity I have in the beginning of the system is going to be the same vorticity I have in the end. And if you want, you can put a little closed thing there. It means it's a closed, integrating across that closed loop. All right, because that loop can deform, we have to use the material derivative here. All right. So the amount of change in circulation is first the time derivative of U in the loop, plus the time derivative of how much the loop is changing. So this is like where, if that loop is like, flowing with the wind, then it's changing in shape. All right, now we have Euler's equation. This is Euler equation. Euler's equation says that material derivative of the velocity is basically, I'm going to divide by rho on this side. And my goal is I'm trying to figure out that each of these two terms is 0. Okay, I'm going to go back to this equation because we're going to have to substitute it in. physically, how much L is changing. So this is dl. This is the rate of change of distance between 2 points, P and Q. So remember that whole loop can deform. So we'll call this P and Q that I drew. The rate of change of the distance between those 2 points, I'm going to just call that basically how much U is changing with L, and I'm going to multiply by the change in distance. So let's plug this in. So remember, I've U dot. I've got U dot that. So I got U dot du dl dl. I can rewrite that as basically the derivative of U dot do U on dl. And I can rewrite that as how much basically 1/2 U squared is changing dotted with the dl component. So putting this together, so the first part, the du dt, I'm going to use the Euler equation, which I wrote above. So I got this dot dl. And this one is 1/2 U squared dot dl. This is how much the quantity is the following quantity is changing, minus p plus sigma over rho. And this is the Bernoulli equation. And we know that's not changing. In other words, the line integral, and the reason why, oh, sorry, this is not Bernoulli, it's just the fact that I'm looking at a closed, the reason this is 0 is because it's a closed loop. Because whatever these quantities are, it's the same in the beginning as at the end. So basically that's not changing around a closed loop. Because, let me write this carefully, because line integral of exact okay. So anytime I integrate something this is called an exact differential because basically everything there can be written as the derivative of something else. So that, if you have a closed loop, anything that looks like this is 0, okay, because it goes and meets itself. All right, so we showed that if you're inviscid, your amount of circulation doesn't change. So this shows that if you're inviscid, the circulation doesn't change. And so that tells us that if flows that are initially irrotational, because there's a relationship between circulation and the vorticity. You'll hear about the words irrotational a lot. Irrotational flows for which the vorticity, remember we call this the vorticity. The vorticity is 0. And Kelvin's circulation tells us if basically if a flow has no vorticity to begin with, you can't get any vorticity later. You can think of W basically as C goes down to basically a point. Gamma, I think, gamma scales as the vorticity. We talked about this a little bit last time. Not last time, but when we did those problem sets involving calculating the omega, calculating this vorticity vector. So basically, these irrotational flows that have this omega being 0, there's a theorem that says if you have no circulation, you can write the velocities as a potential. So for rotational flows, basically they have no curl. And there's a theorem in mathematics that says, and this is also true for electromagnetism and a couple other fields, if they have no basically curl, you can write a velocity potential, which people use the Greek letter phi. Okay. In other words, phi is a scalar function. Phi is a function of x, y, z. And basically, if you take the gradients of it, imagine x, y. Well, this makes a little less sense in 3D, but imagine if you had a 2D potential. Phi is kind of like a mountain range. It's a scalar function, tells you the height of the mountains. And if you know the velocity that you travel, you basically take the gradients of phi. So if phi is really, really steep, I'm going to have a really high velocity. If it's flat, I'm going to have a lower velocity. But all the information of my velocity vector field is in the scalar function phi. And all I have to do is take derivatives to get the information out. And amazingly, a lot of this framework, so potential flows, we know we have conservation of mass. So that means basically all this framework for solving for velocity field, for potentials, is just using conservation of mass, this equation. This is called the Laplacian. So that means the velocity potential satisfies the Laplacian. So for the homework, what we're basically going to do is try to solve for these velocity potentials for a couple. I think we do them for a sphere and we do them for a cylinder, and then we call it a day. I don't give a homework problem on other geometries, but you can also solve it in a wedge or around a plate, and those are just with different kinds of phi functions, which I don't think I'd put on the homework, but we'll talk about it in lecture. So the boundary conditions. So this is really so in when you have inviscid flow, you don't have viscosity. So your boundary is actually going to have like a constant velocity motion, but you still have something what's called no penetration. So this is basically no penetration. It basically means that you don't have velocities going normal to your body. But we don't have no slip anymore because we don't have viscosity. If you do that, then the problem becomes overspecified. So we're going to use the no penetration condition. So this Laplacian, if you read about it in books, this is called a harmonic equation. It has to do with the order of the derivative. So you basically solve harmonic equations using linear means. So a couple things pop out of this idea that the phi, del squared phi of 0, it's a homogeneous equation. It also means if phi 1 is a solution, that means phi 1 plus phi 2 is a solution. They call this equation linear because you can generate new solutions just by adding velocities, by adding potentials. So linear means basically those are ways to solve linear equations. So for example, one is separation of variables. If you remember from the homework, when it was a homogeneous PDE, you could use separation of variables. Complex potentials. Those are for 2D flows, okay? And Fourier transforms. Fourier transforms are especially useful at the water surface. I don't have a homework problem on it, but basically you can solve for these things called traveling waves at the water surface. There's something called a minimum phase speed. If you watch ducks swimming, you can swim basically without too much effort, and then if you try to go faster than your waves, you actually have to go over the little bump in front of you. Like speedboats, so the wave speed, c squared for water waves, I'm just going to mention this now because I don't think we're probably going to get to it. Basically, the wave speed of water, it's c equals the frequency over k, where basically you can use the boundary conditions to solve for this thing called a dispersion relation, which is gk plus sigma k cubed over rho times inverse tan of kh. And this is called the dispersion relation. In physics, it basically means that the length of your waves, which is given by the wave number, tells you how fast it's going to travel. And the amazing thing so the boundary conditions of the water surface lead to you have what dictates the speed of waves, like waves in your pool or waves in the ocean, are dictated by the gravitational constant and the surface tension. In particular, when you're in the ocean waves, you don't care about surface tension, so this term matters. But because omega has a cubic, c has a minimum phase speed of, I feel like it's like around 20 centimeters per second. I can't remember. But there's a minimum phase speed. It's like 20 centimeters per second. So ducks, if they swim so physically what's going on, if you're a duck, you can basically travel at c less than c min really easily. But and you're going to send these waves going backward. But if you basically are a duck and you want to go over c greater than c min, basically you have this thing called a bow wave that shows up in front of you. So you're basically going to have something like this, and you're going to have your duck that's trying desperately to climb over the bow wave, and you basically get slowed down. It's called a bow wave. And these bow waves can only go so fast. So speedboats, they can beat this by basically jumping on the water. Like speedboats, they basically go poof, they basically kind of leave the water by jumping over the bow wave every time. But if you sit on a speedboat, I think it's like your neck is basically kind of in pain. So these Fourier transforms, they lead to all these basically traveling wave solutions. I don't have homework on it, so we're probably not going to get to it. But I think if there's interest, we can get to there. Also, what's really interesting about these ducks, like if you have a top view, there's this wake here. I think this is like an angle of theta is like 27 degrees or something like that. But that's, if you look at wakes of ships and ducks, they're all the same angle. This has to do with how these waves traverse in 3D. G.I. Taylor has a really nice argument about like what sets the width of your wake is at a set angle. Okay. All right. So let's figure out. So we're going to do a couple calculations to lead to show that the drag is 0 on a sphere. We're going to repeat what D'Alembert did, I guess, over 200 years now. Flow on a sphere. All right. All right. So the governing equation for irrotational flow is just conservation of mass. Which we showed was this. And the boundary conditions, one is that the velocity goes to 0 as we go really, really far away from the sphere. Two is that, so this is a little different, that the, basically, if I'm on normal to the sphere, if the sphere was stationary, this would just be 0. Because the sphere is transiting to the right, this normal stress boundary condition says that is equal to the velocity of the sphere dot n. But this is only true on r equals a. So we're going to be using you can consider this to be spherical coordinates. But the only direction that's going to really matter is we're not solving conservation of linear momentum. We're basically just doing this equation. So you have to look up. So if you, I think this should be pretty clear since everyone did the last homework. Gradient and Laplacian in cylindrical and spherical coordinates are different because theta and r, theta depends, everything depends on theta. So del squared phi looks like this. All right. So that's the equation that we have to basically integrate to get solutions. And it was noticed when these early fluid dynamicists did this, they noticed right away that, hey, if my governing equation, first of all, it's linear in phi. That means I don't have like I don't have an extra term. This is all just one term. And I've got these divisions by r. So basically they said, hey, there's lots and lots of solutions, and the sort of most simple one is called the fundamental solution. They call this the fundamental solution because it's r to the negative 1. But that's just arbitrary. And it satisfies the boundary conditions. Basically, you can imagine, remember, gradients of this phi give you the velocity. But certainly, if phi goes to 0, then your velocity is going to go to 0. So very, very far away from your body as r goes to infinity, this goes to 0. All right. And phi to the negative 1. So this is negative 1 equals the subscript. Oh, that looks bad. All right. Let's talk about what linear means. All right, so yeah. Phi is going to have all the information about the velocity. We're going to basically, the way with tangential flows work is that we're going to do all our handiwork with phi, and then we're going to take the derivative of that at the end if you want to calculate velocity fields. So the governing equation in this Laplacian is linear, which means that basically, differentiation, you can basically switch the order. So because of that, you can find many other solutions. All right. And a lot of fluid dynamics is done on spheres because the math is tractable. So what I'm writing here is not really ad hoc because you get to use this for a lot of different problems. For example, so if Laplacian of phi is 0, then I can just take the gradient of phi. And as you know, you take the gradient's a vector. So you take the gradient of a scalar, you're going to increase the order. So it's going from a scalar to a vector to a tensor. So for example, if I take the gradient of phi, which was a scalar, that becomes this. Okay. If I take the gradient of that, this becomes a tensor. There's no dots between those two x's because we need it to be second order. And phi the negative n is equal to del n minus 1 of phi minus 1. So you can take that fundamental solution and yield further solutions. So we have no problem finding solutions to the governing equation, conservation of mass. But the ones that are going to work will be the ones that are useful in solving our boundary conditions. So we're trying to seek a... Remember that solution has to be linear in V. So, the sphere is going at velocity v. We're trying to calculate the velocity field all around the sphere. It better also be linear in the velocity v. And we need to have this information of phi because that is satisfying the conservation of mass. So we choose, basically the easiest way to do that is doing phi is equal to c this times phi to the negative 2. Okay. Where c is a constant. Okay. And I'll tell you right now, the solution to this problem, if you want to plot the velocity field around a sphere, it just looks like negative 2. Gradient phi to the negative 2. And that can be written as c u dot phi to the negative 3. It looks like this. C v over r cubed minus 3 x r cubed. R to the 5th. All right. Sorry, that's all the time we have left. So I will confirm with you next time two things: that this satisfies the boundary condition, that the normal velocity into the thing is n dot v and is equal to n dot del phi, and we're going to calculate the drag, because if you have the velocity field, you can calculate the pressure, and then, well, actually I'm just going to hand wave the drag. You're going to have to do it for homework though, but you basically integrate this across the sphere, across the thing. So new unit, potential flows. Next time we're going to talk about the irrotational vortex, and we're going to start introducing complex potentials. So on the homework, you know enough to do basically the Bernoulli one, the very last one. Who's presenting Wednesday? Somebody's presenting this week, right? Okay, Layla, and maybe someone online, right? If you're going to record something. Okay. And also, your course project phase 2 is due soon. It's going to be Halloween, and that means this course is pretty much over in a month from Halloween, because we just have course project presentations. Rafa, you didn't believe me about this canoe problem, right? This explanation is not super good. You don't remember the last time you went canoeing? It'd have to be like a pretty strong wind. Well, you can imagine in this case, if you're basically have any kind of tilt off this way, if you have any kind of tilt, you're going to have basically this one's going to want to go, this one's going to go back, and this one's going to want to go forward. The stagnation point will be here, and then that's going to give you like a lever arm. That stagnation point pushes you this way, and probably stagnation point on the front is enough to think about it. And then once you rotate this way, if you rotate past it, you're going to have another force going backwards. That's giving you a moment. Yeah, this is stable. So you can still get oscillations around it, but that's the kind of like the equilibrium if once everything dies down. But certainly, so you can consider this to be unstable.
But is that stable because in flow with the viscosity?
When you have viscosity, you have vortex shedding and stuff like that. You don't have this like front and back having the same pressure anymore. But if the wind's blowing fast enough, you consider that to be high Reynolds number, and Bernoulli's okay.
For this problem, we have to consider center of mass as well.
For the homework problem, you have to consider center of gravity and center of buoyancy. For this problem, gravity is going into the page, so it can't dictate what direction the canoe is facing. Oh yeah, this is homogeneous. Yeah, like it's not like you have those toys that go back and forth, because the center of mass and center of gravity are different. Center of gravity and the